It's going to have a little bit of, we wait here for about a minute.
Yep.
Then you will see the actual countdown. All of this at the moment, it gets recorded. It just allows for the timing to work. So the system has a time to catch up.
No problem.
Hello, good afternoon, everyone. It's my pleasure to introduce you to Mark Barnes, Senior Vice President of Global Business Development for Descase Corporation. Today, he will be demonstrating the impact of water on pump reliability. So I'll let Mark take over from here.
Thank you very much, and hello to everybody, wherever you are around the world. It's a pleasure to be here and to share the next 30 minutes with you. As our moderator said, I'm going to be talking about the impact that water has on the reliability of our pumps. And in general, we could think about this as not just pumps, but any rolling element bearing and the impact that that will have on the reliability of the asset. So I'm going to start off by dispelling a myth that we learned pretty early on in high school, and the fact that oil and water being polar and non-polar media don't mix. Well, in fact, they actually do. Water will dissolve in an oil to some extent, and the amount that dissolves will actually depend upon a number of factors. First and foremost, the type of oil. So an oil that has a fairly low additive content, such as a turbine oil, will not really dissolve very much water. But if you go to the other end of the spectrum, you think about something like a heavy-duty diesel engine oil that's as much as 30% by volume of additive. Those additives in general are polar in nature, and they actually help bind the oil and water together. So oil and water do mix to some extent. So how they mix depends upon the type of oil, the temperature, the conditions under which that oil and water is blended together, and so on and so forth. But ultimately, that water will exist within the oil in one of three distinct phases. The first is referred to as dissolved water. So dissolved water, if you were to look at the oil would look nice and clean and clear. It doesn't look like it has any water in it, but in fact, it does have some water. And again, the amount of dissolved water is tied to the type of oil and the type of additives that we have in the system. Once we have a maximum amount of dissolved water in that oil, we reach what's called the saturation point. Saturation point is just the point at which the oil physically cannot hold any more water in solution. Saturation point, again, is dependent upon the type of oil, the type of additives, as well as the temperature. So an oil that is warmer can hold more water in solution than an oil that's cooler. It kind of stands to reason. It's very much like dissolving salt or sugar in cold water versus hot water. When that water gets above the saturation point, the water will exist in one of two distinct phases. The first is called emulsified water. Emulsified kind of looks like chocolate milk. It's cloudy. It's very difficult to see through that oil. It's opaque in nature. And that can be a big problem, because if that mixed oil and water, that emulsified oil and water, is what is lubricating the pump bearings, that really has a really significant impact on oil film strength. It will basically destroy the elastohydrodynamic film between the rolling elements of the bearing. It will also start to destroy the oil life, and it will result in degradation of the fluid. Once we add more water, if the water separates from the oil, it will become free water. Free water is just water that's sitting on the bottom of the oil sump, usually, since water is generally heavier than most lubricants. So that's sitting on the bottom. Sometimes that's a problem. Obviously, it will cause corrosion, but the most damaging form of oil and water is when it's emulsified and when that oil and water mixture is what's actually lubricating the bearings. And here's an impact. So we can see here that there is a direct impact to the machine. So rust and corrosion occurs in cycling pressures. Sometimes we get what's called cavitation, where the water will flash vaporize and create cavitation impacts. Again, as I mentioned, lubricants can be compromised. It can drive oxidation of the oil. Some oils will degrade, as well as additives for that matter, through a chemical reaction. We call that hydrolysis. And other additives prefer to be dissolved in water compared to the oil. So that will cause what we refer to as water washing, an effect where the additives are essentially stripped out of the lubricant and go into solution in the water. And there's an indirect effects. So things like varnish formation, for example, is greatly exacerbated by the presence of moisture in the system, as is corrosion. Water can help drive acidic content within the oil. It can also be a reason for either aeration or foaming to occur. And of course, water is obviously not a good lubricant. So the film strength of the lubricant, the ability of that lubricant to separate moving parts under rolling or sliding contacts becomes significantly compromised. So water is probably second to particle contamination, but it is a very significant impact on all sorts of equipment life, but particularly pumps. The reason being, of course, that with pumps, we are pumping often aqueous fluids. And of course, that water can get back into the pump, or we may get cooling water into the pump. It's often used, and pumps are often used, of course, in applications where water is present. So for that reason, one of the leading causes of pump failure is bearings that fail due to the impact of moisture. Now, of course, it's not just about the amount of water. Again, as I said before, it's the phase of water that the oil's in. So when we think about how that works, there's a term that we use around oil-water mixtures called demulsibility. Demulsibility just is an indicator of how quickly an oil and water will separate. So there are some ASTM tests that we can run to test an oil's demulsibility. But the most damaging form of water, as I mentioned before, is when it mixes in with that lubricant. It becomes a stable emulsion, and the whole of the bearing housing on the pump is literally sitting there with this chocolate milk-like material, and that's what's actually lubricating the asset. So the degree of demulsibility really depends on oil age. It is impacted by contaminants. So if we get certain chemical contaminants in the oil, that can destroy demulsibility. Aging of the fluid, as oil ages, the byproducts of oil degradation can cause that oil and water to bind together and become emulsified, as well as certain cross-contamination issues, either with other lubricants, process fluids, or other materials that are present in the system. So demulsibility, certainly something we want to be cognizant of. Now, part of this is the interaction between the oil in the pump and the air above the oil inside the pump bearing housing. There is a physical law, it's known as Henry's law, and Henry's law essentially states that if the oil is saturated with water, then the headspace will be saturated with water. And we can turn that around and say, if the headspace of the pump housing is at 80% relative humidity, because of the impact of Henry's law, the saturation of the fluid, the oil, will also be at 80%. So one very effective strategy for removing water from oil is actually to dehydrate the headspace within, in this example, the pump. It could be a gearbox, it could be a hydraulic system. But by dehydrating the headspace and making the relative humidity of the air very low, the oil is forced to give up the moisture from solution back into the air. And again, if we dry that air some more, we can effectively remove a lot of moisture from oil simply by dehumidifying the air above the oil in the pump housing. Now, a couple of ways to do that. You can install some kind of dry air purge, and that works for larger volume systems. But the most effective way, certainly for small sump applications like gearboxes, and in this case pumps, is to actually install a desiccant breather. A desiccant breather functions in very much the same way as a small sachet of silica gel that you might find in, for example, a box of electronics or an expensive pair of shoes, where you unwrap the consumer product. And again, you see that little sachet of silica gel, and that's obviously there to help protect the product while it's being stored and transported and so on. So in the same sense, if we can control headspace humidity by exposing the headspace to silica gel, then we can control the moisture in the headspace, which in turn controls the headspace in the oil. Now, what's important here is to think about the saturation point and how that changes with temperature. So there are two terms in humidity we talk about. First is absolute, second is relative. So absolute humidity is how much moisture, typically in grams per cubic meter, how much moisture is there present within the air. So in this example, if we take air at 5 grams or absolute humidity of 5 grams per cubic meter at 0 degrees Celsius or 32 Fahrenheit, that airspace will actually be at 100% relative humidity. That's the equivalent of what we term dew point. So when we think about weather forecasting, for example, we always think about the dew point, which is the lowest temperature at which the water comes out of solution and becomes a liquid. Well, if we take that same air and we heat it up to 86 degrees Fahrenheit, 30 degrees Celsius, the same amount of moisture, so 5 grams per cubic meter, results in a relative humidity of just 17%. Okay, so the important thing to think about with pumps is pumps that start up and shut down, because when they are running and actively working, and the oil temperature may be 100, 120, maybe 140 Fahrenheit, there's a lot of moisture that the air above the oil in the headspace can hold in solution. Once that pump shuts down and cools down, we have a very high absolute humidity. And as that oil cools and the headspace cools with it, there is a tendency for that water that's in vapor phase to come out of solution, and the oil becomes saturated with moisture. The air, the headspace becomes saturated with moisture. We get condensation, and that's when rust can build up and when the oil can start to degrade. So, of course, understanding how much water in the oil is an important thing for us to do. And there are a number of different oil analysis tests we can run, from a simple crackle test where we throw the oil onto a hot plate, all the way through to running a more robust test in the lab we refer to as Carl Fisher. And in fact, the correct way to measure water in oil is to do it through a Carl Fisher method, preferably with the co-distillation method, just to avoid the possibility of any interference from either additives or certain wear metals that can impact. So certainly knowing how much moisture is in your oil is very important, and that's of course why we take routine oil samples. And again, Carl Fisher with co-distillation, is the preferred method. So the pertinent question to this discussion is, okay, every oil is going to hold some water in solution. As I said earlier, all oils will dissolve water to some degree. The question is, how much is too much to ensure the reliability of the pump? Well, this all comes down to saturation. The key to keeping pumps reliable is to ensure that any moisture that is present in the lubricant is present in that dissolved phase. So that means keeping the concentration of water in oil below the saturation point at all in-service temperatures, whether that's 120 degrees when it's running or 50 degrees when the pump is shut down and idle for a period of time. So a lot of studies on this. This is an SGLE publication from way back in the 1970s, looking at the impact of water on bearing life and empirically determining how much water does it take to fail a bearing. So what they first did was to look at the saturation point. So if we take a typical oil that we might use for a standard ANSI style centrifugal pump, most of the time that's going to be an R&O, rust and oxidation inhibited, ISO VG68 product. Sometimes we'll use anti-wear, but most of the time pump oil is an R&O type oil. So if you look at the saturation point, at somewhere around 100 degrees Fahrenheit, the saturation point for an RNO 68, because it has relatively low additive content, will be around 150 parts per million of water. So at 150 ppm, the oil will be completely saturated, which again, due to Henry's law, it will mean the headspace is also completely saturated. So that's kind of our tipping point there, making sure that, again, at whatever temperature we're operating at, we stay below that saturation point. And again, it's really important that we understand this, particularly for pumps that are operating in variable conditions, because as the oil cools down, what may be 500 ppm in the dissolve phase at 158 Fahrenheit, as we cool the oil down at just 68 degrees Fahrenheit, 428 of that 500 has come out of solution and is now sitting free and emulsified in the pump housing. Right? So we want to be really cautious, particularly for applications that are stop-start. So let's think about how that moisture will actually impact pump life. So first thing that can happen, of course, is corrosion. Rust is driven, obviously, by the presence of moisture as well as oxygen. Obviously, anytime we have water in contact with a carbon steel, it is going to generate rust. Obviously, stainless steel, not so much. But if it is a carbon steel, then we are going to get rust and corrosion. Obviously, the thing we need to do is keep that water away from those parts, right? So the first thing is to exclude those contaminants. Now, in some applications, we can also get a different failure mode called cavitation erosion, more commonly found in hydraulics and sometimes in journal bearings. But this occurs when the oil cycles from low pressure, when water tends to vaporize, and then when the oil is pressurized and the water vapor is pressurized with it, we get a sudden condensation of that water vapor, and that creates a microjet of steam that can destroy hydraulic pumps. It can also create etching and corrosive wear, erosion wear on journal bearing surfaces. So it's just another failure mode that we think about. In some applications, this is found in larger rolling element bearings. We can get what's called hydrogen-induced wear. So this is a pretty complex tribochemical process that involves oftentimes our sulfur phosphorus EP additives in combination with water, and that water actually disassociates from H2O into its constituent ions, so hydrogen as well as the hydroxyl ion. The hydrogen ions are actually very small, of course, and they can migrate into bearing surfaces, particularly if there's any initial cracking, and it creates what's called hydrogen embrittlement. This makes the surface very brittle, reduces the fatigue strength of that metal, and it can create cracking. There's a term that we see quite commonly, particularly in wind turbines, called white etch cracking, which is a phenomenon that's driven by this process. Now, if we think about bearings in particular, rolling element bearings such as we find in pumps, of course, work on the principle of elastohydrodynamic lubrication. That means that we want the oil to have a very high pressure viscosity coefficient, meaning that as the oil flows through the load zone of that bearing, the pressure that is exerted on the lubricant turns that lubricant from liquid to solid, thereby creating the elastohydrodynamic wedge. Well, water has a very significant impact on the pressure viscosity coefficient of a lubricant. As I mentioned before, it can create hydrogen embrittlement as well as etching and corrosion within the system. So water really is a driving factor, a significant driving factor behind pump life. And in fact, if we look at the life expectancy of a rolling element bearing, so on the y-axis there, we have the relative life of a rolling element bearing compared to the water concentration in the lubricant. You can see that as we go from the right-hand side of the graph, where we've got very high water content, as we start to reduce the water content, initially there's not a significant change in life expectancy of the bearing. And that's because between 500 and 150 ppm, any water that's present is going to be present in the free, or more commonly in the emulsified phase. And that means that the elastohydrodynamic film cannot form correctly and the bearing is going to fail. So we see very little impact. It is not until you reduce the water concentration below the saturation point that you start to see a significant impact on bearing life. And as you can see, as you get drier and drier lubricants, the life expectancy increases exponentially. So as reliability professionals, lubrication professionals, our job is to ensure that we keep our water content as far to the left-hand side on this graph as we can if we want to maximize the life expectancy of our bearings. So how do I do this? How do you actually improve the life expectancy of the bearings? A couple of ways we can do that. First of all, know it's there. So you can install, as an example, a simple, what we refer to as a 3D bullseye, which replaces a standard flat-face bullseye or a BS&W, bottom sediment and water bowl on the bottom. This typically hangs below the bottom level of the pump and allows us to see the buildup of free water. And you'll see the picture on the bottom left there shows some water in a BS&W bowl. That's actually standard now on the new API 610 pump standard. So anybody that's on the call here from the refining and petrochem industry that is working according to API 610, this is now a requirement, a recommendation as part of API pumps. But that obviously is just an indicator, right? Tells us we have a water problem. The best way to control water, as I stated before, is to get that headspace dry by dehumidifying the air above the oil. And as that occurs, the water will liberate out of the oil, and it will be adsorbed and removed by the desiccant breather. Now, one of the common questions and one comment I often get at this point in the presentation is, yeah, but we have pumps with bearing isolators. So we're using Impro seals or other types of labyrinth seals that are designed according to the IP66 standard to exclude particles and moisture. Well, the reality is the IP66 standard is really a standard that measures the ingress of liquid water. It doesn't have any relevance to how the humidity in the working environment of the pump can migrate into the bearing housing. So you will hear incorrectly people state that with bearing isolators, you don't need to have any kind of moisture control. You simply put the plug in the fill port and you can seal it up and the bearing isolator will take care of it. It's simply not true. Any moisture in the operating environment can and will migrate through a bearing isolator, and you will find that the headspace of the air inside the pump will be humid, meaning the oil will also be saturated. If you don't believe me, this is an example. This was a trial, a test that we ran in Florida. So obviously in Florida, very hot and very humid environment. So on this particular day or week, I should say, for testing, ambient temperature was around 93 degrees Fahrenheit, 74% relative humidity. And quite simply, we equipped two pumps, one with headspace humidity control, the second with no headspace humidity control. And you can see the data is pretty clear. That pump on the top right there that has no protection from headspace humidity maintained a relative humidity of around 50 to 60 or 65% RH. And you can see there are regular periodic spikes corresponding to the 24-hour period. And of course, when temperature increases or decreases daytime, nighttime, you're going to see a change in that relative humidity because of the impact of temperature on saturation. By contrast, you can see the pump on the bottom right that was protected with a desiccating breather, maintained a very low relative humidity, very close to zero. And that translates, according to the previous graphs, into a very significant decrease. So this is just an idea of what can happen inside that pump housing as that breather is adsorbing moisture. So if we relate this back to the life expectancy of a bearing, again, when we're controlling headspace humidity, typically we're going to be below 40% RH. That means our relative bearing life is going to be, on this graph, above 140%. Whereas if you're operating on the right-hand side, your relative humidity is, up around 70, 80, even 90 or 100% RH. You have a significant reduction, perhaps as much as a 30% reduction in bearing life. And it's all related to the saturation of the oil. So again, we want to make sure that any oil that is in the pump is maintained at a level of moisture that is below the saturation point. And it all comes down to what temperature is the pump operating at, what is the ambient operating conditions, and how does that ambient temperature fluctuate with time. So as a takeaway, we're getting close to the end of time. I want to leave a few moments if there are some questions, but as a key takeaway, how do we help ensure that we maximize the life expectancy of our pumps? A lot of people in the refining petrochem business and other industries pay very close attention to the mean time between failure of pumps. Old school technology where lip seals were used to protect pumps really didn't have a very effective job at controlling pump life, and maybe our MTBF under those circumstances was as low as 2 to 3 years. Over the course of the last 10 to 20 years, the use of labyrinth seals bearing isolators have become widespread, and that's obviously a very good thing. And people that are really performing very well under those conditions often see MTBFs in the 5 to 7, perhaps as much as 8 years of life. The best case scenario, if we protect our headspace, both with the use of bearing isolators as well as desiccating breathers to dehumidify the headspace, that will give us the maximum potential and the longest bearing life, which of course should translate into the longest pump life. So with that, we do have, I think, 5 minutes remaining in this session. So I'd like to turn things over back to our moderator to see if there are any other questions or any questions from those that are participating.
Thank you very much for the presentation.
It's my pleasure. Do we have any questions?
Is there a question? Earlier, Dugard asked, are there on-site control techniques that can be used to check the level of water in oil? I think you addressed some of these clearly, but
yes.
Would you like to comment further?
Yeah. So if I understand the question, is there a way of measuring the level of moisture in the field on site? Is that correct?
Yeah, that's how I understand it.
Yeah. Yes. Well. There are. The problem is that most of the tests that we run in the field, for example, there's a calcium hydride test kit we can run. There are relative humidity probes that we can use. The problem is that those really are not measuring the concentration of moisture. They're really just measuring the relative humidity or saturation point in the oil. In the case of the calcium hydride test kit, it really doesn't pick up moisture until that water is essentially at 100% saturation. So unfortunately, today, the most rigorous method is still bottle sampling and submitting to the lab for the Carl-Fisher test. But there are some test kits that look at calcium hydride, as well as I said, a temperature probe, a relative humidity temperature probe, or there are actually some field FTIR instruments. But generally speaking, lab analysis is the most accurate method.
Thank you for that. I think you addressed a question also of Kevin Albert, who had the same question. Any other questions people like to share through the chat? And by the way, Vanda, Patricia DuFranco gives you her thanks for the presentation.
Thank you very much for participating, everybody on the call. No other questions?
I have a quick question. At what point do you go for like a bigger solution? When do you decide to go from, say, to a vacuum dehydrator?
Yep. Yeah. So the strategy, obviously, for most pumps that we're talking about here, small ANSI pumps, the volume of oil is relatively small. But as we get larger and larger in volume, so for example, as we go to gearboxes, a better strategy, well, still using a desiccant breather is a good strategy, but if you want to remove moisture, there are filter elements that contain what's referred to as a super adsorbent polymer. Chemically, it's very similar to what we use in baby diapers. So you can actually set up a filter cart that has a SAP filter. Sometimes you can buy pleated filters that are impregnated with SAP as well, and they will help remove moisture. They really only remove free and emulsified. Again, they don't remove water down through the saturation level. To your point, if you really want to remove water down to a very, very low level, the only practical way to do that really is through vacuum dehydration. The challenge, of course, is even the smallest vacuum dehydration units are very expensive. They're designed obviously for larger turbo equipment. So, it really comes down to what's the volume of oil and how low do you need to be from moisture perspective. But there are solutions at every end, from small wet sumps like pump housings through kind of, we call them medium-size gearboxes and small hydraulic power units, all the way up to our turbo machinery, where of course we've got thousands of gallons. So there are solutions to deploy at each stage.
I think we have time for one last question. Are these test kits available on site for on-site analysis?
Yes, there's a number of vendors. If you go online and search for calcium hydride test kit or water and oil testing, there are a number of suppliers of instruments that you can use on site. So there's plenty of good information online that you can find. If you don't find, whoever asked the question, don't find what you need, please feel free to reach out to me through the platform or directly, and I'd be happy to point you in the direction of vendors of products that will work for you.
Great. Well, thank you very much, Mark, for this very interesting presentation. And this will adjourn us.
Thank you very much, and everybody have a good rest of your day.
Thank you. Bye-bye.